Good morning, everyone, and welcome to the second day of the GMAP Winter School. This is the first day we are going to look at the geologic mapping directly on the data on the geologic maps as GIS. I'm Alessandro Frigeri. I'm a researcher. I work here in Rome at the National Institute for Astrophysics. I'm a geologist by training, and I've been involved in several missions in the last now 20 years. Mission to Mars, like Mars Express. I've been involved in a NASA Dome mission to Vesta and Ceres, and now I'm working as a researcher here at INAF, working to the forthcoming mission to Mars, ExoMars, which has been delayed to 2028, and I'm involved in some proposal for mission to the moon. So this second day we will be facing the geologic mapping of a small body that we will see that has been discovered relatively recently, let's say. In the first part of the day, we will analyze three different aspects of the same problem. Or well, we will face geologic mapping of a body like Vesta. We will learn about impact crater chronology and its importance to dating materials, but more importantly, processes that follows one each other and build up the evolution history of a body, of a planetary body or a small body. And then we will look at the surface composition with some data that comes from the spectroscopy. As we saw yesterday from Christian, how important is spectroscopy in planetary science, but in general in science, how looking at the spectra is critical. So I will introduce the exploration of Vesta. Will give also a brief introduction to the geology of Vesta and geologic mapping of Vesta. We will see also the data set that you have available, and you will work on that for the exercises. And then colleague Roland Wagner from German Aerospace Center will tell you more, will speak you about chronology. He's a real expert, and you are lucky to have him as a teacher, because he's very good in crater chronology. I'm sure that you will learn a lot with Roland. Then, in the third part of this first slot, Katrin Stephan from the German Aerospace Center, also an expert in spectroscopy, will tell you about the surface composition of Vesta and the data set, which is called the Snowman, and we will see why it is called the Snowman. And then at the end of the day, we will have the afternoon seminar, as we did yesterday. So let's get through the first part of this day together, and let's speak about the geology of Vesta. So we will learn about the exploration of Vesta through time, which has been something really amazing from the scientific point of view, and I'm hoping that I will be able to communicate to you how important was this discovery and how exciting it was for a scientist to be following this kind of exploration. In fact, we will speak about this mission, which is NASA Dome, which has been developed for years, and it was active 10 years ago, and gave some really interesting results about Vesta and Ceres. And then another point which is important is that we will get through reading the geologic map of Vesta, because geologic mapping is important and is fundamental, as we heard from Matteo yesterday. And the more the geologic map is readable by non-geologists, the more we will be good at it, and we will be able to communicate all the analysis that we are doing with the geologic mapping and with the interpretation we are applying when we are mapping. Then we will take a short break, and we will get hands dirty on the GIS data set. So we will get through the GIS, the geospatial data set you have. We will play with we will switch QGIS on, as we did yesterday during the tutorial of Riccardo and Luca. Just one thing that I asked to check. Please check that you have downloaded the version 3 of the Vesta Snowman, which has been available since January 18th at the school link. So if you downloaded, for example, before January 18th, please download the most recent version, because it's much more improved, and you will be able to follow along what we will be doing in the second part of the first lot of the day. Then we will see assignments for next month, because on one side we will speak about what is the process for making geologic mapping. Of course, the school is not just for learning geologic mapping means like staying it will take like a year at least, but it will be important for us at least to know the importance of geologic maps and to know the process we use to produce geologic mapping. So that will help a lot. So the assignments will be given to get you more used to the process of producing that. Okay, so let's start to have an idea of what is Vesta. Where is Vesta? So Vesta is a body of is one of the actor of the solar system, let's say, of our solar system, and it is located in the so-called main asteroid belt, which is the space within between Jupiter and Mars, where a lot of debris orbit, and in particular, Vesta is the second most large body of this asteroid belt, with a radius of 255 kilometers, roughly. So it's pretty big. And since it's pretty big and also pretty bright, it is possible in favorable condition to observe Vesta at the naked eye, as we see here. So Vesta is a body that can be seen directly from Earth on the asteroid belt. And so this means that it attracted the curiosity, let's say, of scientists. And the first observation of Vesta dates back to 1807 in Bremen, in Germany, where the astronomer Olbers observed for the first time Vesta. Or well, observed for the first time a body, and then this is an example of like interdisciplinary science. The astronomer asked Gauss also to compute the trajectory of this body, and it turns out that Carl Gauss was honored to put the name to decide to give the name to this body, and this body was called by Carl Gauss Vesta, after the name of the goddess of of the house, the family, and the earth in the Roman mythology. So in this painting, we see one of the rare example of Vesta represented as a woman, and this comes from Pompeii, and this is one of the rare example of where Vesta is represented as a woman, because it was usually represented as a flame that was protecting the house, the family in the Roman culture. So now that we know something about Vesta, we know something more about Vesta, that this object was discovered by scientists, by the science in the 19th century, and it was named. So basically, it was a point in the sky and had a name. In the 20th century, technology evolved. Let's say we had a lot of evolution in technology, and especially spectroscopy or reflectance spectroscopy evolved a lot in the 20th century. And as we learned yesterday from Christian, reflectance spectroscopy deals with the interaction deals with the study of the interaction between the light and the matter. And basically what happens is that in the 20th century, some telescopes were able to detect the absorbed light from bodies in the sky, and so astronomers were able to receive spectrum of the bodies of the observed bodies, and with the spectrum, as we saw yesterday, we are receiving a fingerprint. What is the equivalent of the fingerprint for a person? So a spectrum, for example, of a body in the sky gives us the fingerprint of the rock of the body is made of. So the use of reflectance spectroscopy for Vesta was the key for this big discovery in 1970. When the astronomer Tom McCord observed that Vesta contains a strong absorption band centered near 0.9 micron, almost 1 micron. And in that years, that was very interesting, because with other researcher, we also observed that Vesta exhibit absorption band in the 2 micron band. So this gives the fingerprint of Vesta, and in particular, this fingerprint with these 2 absorption band, as we saw yesterday from Christian, are typical of pyroxene. And pyroxene is a mineral that is typical from, it is the typical results of a melt. So on Earth, the typical result of a melt of a silicate is the basalt, for example, the lava when it's flowing outside of a volcano. So as geologists, we think in terms of processes, but it's evident that if we observe in the asteroid belt, which was thought to be like a pile of rocks, just debris, we observe basalts, we start imagining that body was probably something different from a bunch of piles of rocks, but probably there was some geologic process going on. But what's incredible for that is that the absorption band that has been observed with this reflectance spectroscopy from far correspond very well, fits very well with some meteorites we have on Earth. So this is a big discovery. Oh, well, this puts the science in front of something very important. Or, well, it enables, or, well, it builds the hypothesis that probably Vesta is not a pile of rock, but Vesta is something that is made of these eucrite, diogenite, and awardite, which are the meteorite we have on Earth, and that fits very well the spectra of this body. So the second step in the discovery, in the knowledge about this body, comes in the 20th century. The reflectance spectroscopy applied to Vesta builds the hypothesis that some meteorite on the Earth are probably coming from that body, and that body is not a pile of rock, but is a differentiated body. Of course, technology evolves. Technology evolves like we saw from the 19th century to the 20th century with the spectroscopy, and then the telescopes evolved as well. And then with the Hubble Space Telescope, it was possible to observe even better the Vesta, the body of Vesta, and the spectra of Vesta, which we see here in a picture in an image of Hubble Space Telescope from 2007. And we start to understand that the surface of Vesta offers different colors to the viewer, and so the body starts to describe itself as a differentiated body and not just a pile of rock again. And now in 2007 happened something else, which is this one.
12, green status 4, 10, 9, 8, 7, 6, 5, 4, 3, 2, main engine start, 1, 0, and liftoff of the Delta II rocket with Dawn using ion propulsion to reach the catalysts of our solar system.
All right, so technology evolved. And so in 2007, when Hubble started to offer that images of Vesta, we launched a mission to Vesta and Ceres, to the asteroid belt. It was the NASA Dome mission to Vesta and Ceres, which has been developed by NASA. But what is interesting is that it is the first mission that visited the two different bodies in the asteroid belt, and also it is a mission that express really international effort, because the scientific payload of this mission comes from 3 different countries, and in particular, on board of NASA Dawn, we had a camera that comes from Germany, from Europe, Germany, and then we have a spectrometer, which is the equivalent of the telescope used for observing Vesta from far, but it is a mapping spectrometer, meaning that it's able to map the surface of Vesta in the hyperspectral range, as we saw yesterday from Christian. And then another instrument is coming from the US, and it gives the information of the presence of hydrogen, so that it detects the presence of water from the surface. So yesterday, Angelo showed us how the data has been put together. And this video shows the mechanism of remote sensing. So for those of you who are not into remote sensing or planetary science, this is the process, basically. We orbit around the body, and the instruments acquire the data over the surface, and each chunk of data is tied together to produce a synthesis, or to produce assembled data product. And this data product are the results, basically, of this research. So when it comes to the mission, to the exploration of during the mission, the instruments acquire data during time, and then the science team, or well, all the scientific activity around these instruments reduces this data and try to synthesize this data into a common visualization, let's say. And so those are the first big results of Vesta coming from NASA Dawn. Those are the results from the camera. So what you see is a simple cylindrical projection. We saw yesterday from Angelo what it means. It means that we are seeing all the surface of the body of Vesta projected over on a plane that has been developed over a cylinder. So we have a bit of distortion, but as we saw from the craters, for example, but we have a view over all the surface of Vesta. And what is amazing is that we start to see things, of course, and we see craters as we are used on the moon, and that's not big surprise, let's say. But also we see lineation, or well, linear features. And these linear features are interesting because geologists knows that when we see lineation, they mean something in terms of processes. And so also, what we can observe is that the surface, the color, or well, the albedo, or the reflectance of the surface varies with from area to area. And this is also interesting because it may be related to different materials or different physical state of the surface. So the results of NASA Dawn at Vesta shows that Vesta has a lot to tell from the geologic point of view. And so those are the results from the camera, so from the imaging. But if we take the camera and we process the camera using a technique called stereoscopy or photogrammetry or stereophotogrammetry, and we use a couple of overlapping frames of the camera, we can detect the elevation, and then we can produce the topographic map of Vesta. And this is a representation, a color scale representation, a shaded relief, as we saw yesterday of Vesta, where we can observe and we can read basically the topography of Vesta, which ranges from minus 22 kilometers to plus 19, which, if you think the radius of the body being 255 kilometers versus 7,000, for example, of the Earth, this means that the range of elevation is huge. The range of topography ranges a lot on Vesta. And this is another element that suggests us that these bodies has been interested by a lot of processes or very violent, let's say, events that as a geologist we try to understand and to detect and to put in order in time. So another element that I forgot to tell you before is that as soon as we go to a place and we start to detect features on a surface, we have to name them. So nomenclature is important for, let's say, for humans, because as soon as we see something and we recognize something, we have to name them. So Vesta, as soon as we arrive there, need a nomenclature. And nomenclature is fundamental, because with nomenclature we start to name things and to communicate among the scientific, for example, the scientific community, and we can start to study these things. So, for example, if we want to study this Hopia, once Hopia is a name and not just a coordinate, Hopia starts to be more familiar to us, and this is the way that exploration works. Since the beginning of history, we start to name things when we explore, and this is happening also in planetary exploration when we face new feature in new planets, in new worlds. We start to use nomenclature and to name these things. And so Vesta has got an official International Astronomical Union nomenclature, which can be found in the Gazetteer of Planetary Nomenclature, is standardized. And one particular thing of Vesta is that all the features there are the Vestals, are named after the Vestals, which are the women that were devoted to Vesta goddess in the Roman culture. So you will see this typical nomenclature over Vesta a lot. So back to the topography. Now that we know that we have features, we name features and we recognize features, we can start to behave like geologists, at least, because we start to ask questions. So why this body has this big range of topographic jump, let's say, and why the features we see in this, the linear features are concentrated along the equator. And for example, why there are these three craters put together like one next to each other. So those are the questions that are obviously coming once you put together these data, and those are the driving questions for getting into the geologic mapping, the curiosity that brings us to map things and to try to define the reason for the existence of these features. So I want to spend some words about the use of cartographic projection. Yesterday, Angelo explained very well the idea that the cartographic projections on one side are useful, or well, they are useful because on one side they distort the data, but on the other side, if you use it wisely, you can understand the data better. So in this case, we are dealing with a simple cylindrical projection, and so it is possible to observe very well the feature at the equator. So we are starting to see that the equator, Vesta shows this lineation, and these lineation are all over the equator. Some lineation over also on top, on the oriental part, but mostly there. So, of course, we will be curious about seeing what's happening here in the south. But in the south, the distortion is very big. Just think that we assume that the craters are circular, and when we are next to the South Pole in a cylindrical projection, the distortion is enormous. Is not useful to describe what's happening there. So we can use different projection. So This should be the mole-wide projection. So we started to see all the surface. So we are still seeing all the longitudes of Vesta, but we are trying to minimize the formation through the South Pole. So basically, what we start to see is that in the South Pole, something's happening. A very, very big hole, or well, big depression is at the South Pole, but next to it, we see that there is also a big mountains or a big chain, like here and here. So we change completely the projection, and we use what we saw yesterday, the stereographic projection. So this is the stereographic projection centered in the South Pole of Vesta, showing the topography of Vesta. So what is amazing is that by using the correct cartographic projection, now we are detecting something else. We are seeing a circular feature, let's say, with a mountain inside. And what's amazing is that within, let's say, 100 kilometers, the elevation passes from minus 20 kilometers to almost 15 kilometers, which is a lot. Just to have an idea, this is called the Rea Silvia Basin. And just to give an idea, this mountain is basically as big as the Olympus Mons on Mars, which is the biggest volcano in the solar system. But we are in a body which is 255 kilometers of radius, so in a very small body. So this means that this is the results of something, and this something has been modeled as a big, huge impact happening in the first part of the life of Vesta. And this is a simulation. This is a numerical simulation of what can happen to a body when an impact of a really, really big impactor occurs on the surface. So this is the effect. Basically, an impact can affect all the body, and we can appreciate from this animation the idea that from the shape, from the morphology, we get an idea of what is happening, and then we create a model for that. So this is a process that is happening always in science and scientific research, and so this was one of the outcomes from the observation of the morphology to the creation of the model. But there is more. The more you see this data, the more you advance in the knowledge of what you think are the processes happening. So after knowing the Rea Silvia Basin, after getting known to this kind of huge impact, what was interesting, it was that the fractures that we were seeing in the equatorial part were not pretty in the right position with the center of Rea Silvia. And so by observing again the topography, we started to understand that the other fracture, the fracture we were seeing in the equatorial part, were probably put in place by another basin, by another impact that happened far before the Rea Silvia Basin. And so we start to be geologists, let's say, or well, for those of you who are not into geology, you must know that every time the geologists do an analysis on morphology and the interpretation is which is older and which is younger, and we use every kind of information. We use like topography, morphology. We use, for example, isotopic dating on, we will see with Roland, we will use crater counting, for example. But the key in the geologic interpretation is to travel back through time without having under our hands the material of the experiment. So we are basically reconstructing back the history, the evolution of the body. So that was really interesting in my opinion, because that shows that what was considered a bunch of rocks started to be interesting geologically. And let's come to the spectroscopy. I will not spend a lot of time because Catherine Stefan will speak you a lot about this, but what is functional to the geologic mapping is this one. This is a graph of that two parameters, let's say. Yesterday we sorry, we heard about spectral parameters. And so the band center and of the two bands are here represented like in gray, the mission dome, the spectrometer here on the mission dome. And then the dots are the spectroscopic observation of the meteorites we have. And so without entering into details, we were able to classify the map of Vesta in terms of the three meteorites we have in hands here on the Earth. And so the results have been published in 2018. Oh, sorry, in 2008. There is an error here, or 2018. I don't remember. No, 2018. And this is the lithologic map of Vesta. And this is important because we see here the white line, sorry, is the projection of the Rea Silvia Basin. And we see that basically the surface of Vesta is mostly made by eocrite and auardite, which is basically basaltic and a mixture of basaltic and non-basaltic. And where non-basaltic, or well, non-eocrite, sorry, meaning diogenite. Diogenite is the part of the HAD that comes from the mantle. So as soon as we see more yellow material, here we have some red, it means that we have mantle material or material from beneath exposed on the surface. And that is also important to understand the geology. So with the geology, we start to put everything together, usually. The geologists used to be really, really interested in several things because it used to merge observation and the investigation starts to be interesting when there are several aspects of the same problem that converge. So from the observation of the camera and from the observation of the spectrometer, we observe that basically impact cratering is the main geologic process at Vesta, with some secondary processes that today we cannot face, but basically the impact, for example, of Rea Silvia is an impact, but it generates, for example, tectonics on the equator. So it is the main process, let's say. So impact cratering is everywhere in our solar system. For example, the moon, we have the moon under our eyes every time, and we can control this. We have under our eyes a beautiful example of impact cratering, but also we have impact craters also on Earth. For example, this is the meteor crater. And this impact crater is a friend. Impact cratering is a friend of the geologists, because if we create a model of impact craters, we can think about impact cratering like a bulldozer that excavates material from beneath and exposes the material outside. So without entering into the details, if we have to group the material, the craters in our solar system in two families, we will have the simple crater, the so-called simple crater, and complex crater. Depending on the body, we will see both of them in every body of the solar system, let's say, almost every body of the solar system. And so the difference is that in the simple crater, we have an impact, and the impactor crunches the crust or destroys the crust and melts a bit the crust and exposes and put the material around. So it makes the favor for the geologists, because it exposes the material outside around the crater. And so those are called ejecta, and the ejecta are important because they are a representation of what was here. The complex crater, I think that now it's evident that Rhea Silvia was a big, huge, complex crater, or, well, in that case, we are facing, if we have to be technical, towards a basin, but the shape is the complex crater. When the impactor starts to be big enough, the energy is so huge that part of the crust melts, and we have this rebound of lower material that crystallize at surface, and it shows like a central peak. So what we were seeing before in the topography and then in the model that has been produced is this rebound. The rebound exposes rocks from beneath on the surface. So those are models. Those are models that are very useful to the geologic analysis, because as soon as we recognize these models, we start to understand, or, well, we think that we are understanding these mechanisms here and there, and we start to put these together within a time framework, let's say. So it's time to take a look to the geologic map, but before, we have to understand the ingredients of the geologic mapping. So at it more, let's say, basic level, to do a geologic map, we need base maps. Base maps are instrumental data, and in this case, or, well, for the geology, we need a response from the surface in terms of radiometer. So an image, or in the visible or not visible, the image gives us the idea of the surface texture and the surface, and we can make hypotheses on different composition of the surface. Then we need also the topography, because the topography, let's say, give us the vertical, or, well, give us the topology of this difference of material, of composition of what we make hypotheses of being different materials. And so the topography is fundamental to understand the spatial relationship in 3 dimensions between these different materials. So the ingredients are base maps, which are instrumental. They are coming from the instruments, and so they have to be put together. We have to trust this data, let's say, but they are the base for the interpretation. So the interpretation is, it cannot be automatically. It is made with experience. We can start from simple and then go whenever we want. And it is, let's say, the soul of geologic mapping. And so how do we communicate this interpretation? We communicate this interpretation in terms of symbology. We use the specific symbols, so geologic mapping is really relying on symbology a lot, because the symbology is fundamental to communicate what are the materials and what are the sequence of these materials in time. And what does it mean? It means that this is the geologic map of Vesta, coming from all the instrumental observation, all the interpretation, and the communication between also geologists, scientists in the science team. So this is the first version, or well, the first geologic map of Vesta came out after, just after the first results. And I want to read this map with you, because on one side, for doing geologic mapping, you need geologists, you need experience, of course. But on the other side, reading the geologic map is something really important and must be done not only by geologists, of course, but it has to be usable by other scientists. Because in this case, the geologic map of Vesta synthesizes all the evolution that we observed in the previous slides with all the data. Yesterday, Riccardo told us that geologic units are usually represented in the legend from the older to the younger. And that is true. That is very true. And this is a standard, let's say, de facto standard. Here, I show you the geologic units in a very simplified way, or well, the legend of the geologic units is very simplified. Usually, we deal with the not just a simple legend like that, but we deal with so-called correlational map unit, where units are relationship can be complex. But in this case, we want to understand what the geologic map of Vesta tells us. So we see different colors, and the colors are linked to the so-called geologic units. The geologic units are something that we define as volumes of rocks or materials that we map, and we think they have been put in place by the same process in a limited time span. And this is the key, because with the geologic map, we are not seeing just the surface, but we are seeing the subsurface, or well, we are seeing in 3 dimensions, but also we are seeing through time. And so reading the geologic map of Vesta means that we can start, as Riccardo said, from the older unit, which is these brown pre-Venerian crater islands. And we say, okay, the northern hemisphere of Vesta is pretty old, or well, is the older part, is the older region. And then now that we know that we can get through the time here, we look that this purple stuff is directly on top of that, and is let's say, is related to something that happened just after the brown thing. And if you see the name of these guys, we are calling pre-Venerian and Venerian Saturnalia Fosse formation. So you remember before we saw the Venerian basin, Veneneia basin, which was the pre-Ria Silvia basin. And so in the geologic map, we see exactly that. The Saturnalia Fosse formation, in this case, is a tectonic formation. So it's not material, it's not just compositional, it's a formation made by structures. And we define that because it's important to record that in the geologic record, in the geologic map. And so that's the expression of that. And they are placed in the middle latitude, the north of Vesta. And so we go through Rea Silvia, and then all the blue units are related to the Rea Silvia, the big impact we saw before. And then we go through the yellow material, the more green and yellow material, and you see that the yellow material are related to the crater, and this is typical. So the craters are continuously eating the surface, and as we see before, around the crater we have this crater-related material, which is over all the craters all around Vesta. So the bottom line is that the geologic map is not just a bunch of colors for experts, but it's something that, if it is well done, it tells the history of the evolution of a body or a region of a body, like we do it on Earth, we do it on the planet. Another element is, once we know the geology, or well, once we are able to tell a geologic history of a body, we can also build a model. And so this is the model, a three-dimensional model of Vesta, and nowadays we consider it as a valid model. So since the beginning of exploration, since the first observation, we find that Vesta, we had the hypothesis that Vesta is differentiated, and this is the model where we have a core, a mantle, and a crust. And all the geologic observations are supporting this idea until there are new observations, or well, there are new updates on this science. So, conclusion for the exploration of Vesta and the geology of Vesta. What is amazing, and what I think is the main message here, is that in 200 years, in almost, or well, yes, in exactly 200 years, because it was, let's say, 1807, in something more than 200 years, we started from not knowing a body to discover it, name it, building a scientific hypothesis about the idea that for the first time we had in hands the sample. So it was a sample return that, on the contrary, it was the contrary of sample return, because we had something in hand and we wanted to verify that something, the HED meteorites, were really coming from that body. And so we passed from an unknown object to an object with an official nomenclature. So on Vesta, we name things like we name on the Earth. And particularly, we discovered that NASA dawn really confirmed that Vesta is the dawn of the solar system. So it is this intermediate body between the asteroid and the planets. And another point that is really important is that we were able to do the geologic map of Vesta, describing the evolution through time, and now we are able to define a model of this body until we go for further analysis. For example, just imagine a landed mission to Vesta, what will tell us in future.